one or two simple problems, then we go more into more complicated problems that include many issues. Okay. So since we are in no load state, we said in the transformer tests that in open circuit test or in no load states, all the power consumed or by the transformer will be dissipated as core losses. So this is the power consumed by the transformer in this state. So all this power, or the most of this power, will be consumed as a core loss. So it will be dissipated in the core. And we know that the core losses are the hysteresis losses plus the eddy current losses. Generally, in the no load state, we neglect the copper losses or the ohmic losses. But in these problems, the no load current seems important a bit. 1.4 ampere is a big value. That's why we can calculate also the copper losses, and the core losses. So since the power consumed in this state, so the core losses equals to what? Equals to the no load power 80, which is given, minus the copper losses, and the copper losses equals to what? P copper equals to the current, the resistance times the square of the current. Here we only have the primary resistance because the secondary is open. We have only the primary resistance. So the copper losses equals to what? Equals to 1.4, which is the current square, times 0.5, and the core losses equals to 79.5. So it's almost equals to the no load power. Just in this case, we have considered the copper losses. In other cases, we may neglect them if the no load current is too small. The second question is the no load power factor. So the power factor can be determined from the apparent power. We know that the active power is the current times the voltage times cosine phi, and the apparent power is the current multiplied by the voltage. So the cosine phi equals to what? Equals to P over S or P over VI, and it can be, since the apparent power here is the voltage and the current are given, so we can calculate the apparent power, and the power factor, the no load power factor, equals to 0.476. The last question is the maximum core flux. For this, we can use Faraday's law to calculate the maximum flux. We know that the EMF, the induced EMF, here why they said neglect the primary resistance and reactance. In order to take the voltage as it is. Okay, in order to take the voltage as it is without neglecting, for example, without considering the voltage drops that maybe affect the input voltage. So in order to take the voltage as it is, we know that according to Faraday's law, that the induced EMF equals to what? E or V. If we neglect the voltage drop, equals to E equals to V, and equals to 4.44, and we have proved this, times N times F times phi. So phi equals to V over 4.44 times F times N. V is 120, frequency is 60 Hertz, and the number of turns is 480. So the flux equals to 0.94 milliweb. Okay, so this is concerning the problem number 1. I think this problem is simple. We have only direct applications to some laws that have seen in our course. Let's pass to the problem number 4, which is more complicated than the previous one. Problem number 4, the parameters of the equivalent circuit of 100 kVA transformer. Always you see that the transformer always is defined by its apparent power. The high voltage is 2400 volt and the low voltage is 240 volt. So it's a step down transformer. So this is the equivalent circuit of the transformer, and we can see this is a general equivalent circuit. It's not referred to the primary or to the secondary. Okay, so those the parameters of the equivalent circuit. R1 equals to 0.2, R2 equals to 0.02 milli ohm, X1 equals to 0.45 ohm, X2 equals to 4.5 milli ohm, RC, which is the core resistance, equals to 10 kilo ohm, and XM, which is a magnetizing reactance, equals to 1.55 kilo ohm. So using the approximate equivalent circuit referred to the primary, determine the voltage regulation and the efficiency of the transformer at rated load with 0.8 lagging power factor. So let's start by the voltage regulation. We have seen that the voltage regulation is a percentage that equals to what? To the voltage, the difference of the voltage at no load state minus the voltage in the load state over the voltage in full load state. Let's try to use a table. Okay. 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 We have seen that the voltage drop equals to what? The voltage regulation percentage equals to the voltage in no load state minus the voltage in full load state over the voltage in full load state. The voltage of the no load state minus the voltage in full load state equals to the voltage drop, delta V. So equals to the voltage in full over delta V over the voltage in full load state. So the voltage regulation, we said that it can be positive, it can be negative, according to the type of the load. If if the power factor is lagging power factor, the voltage regulation is positive. If the power factor is leading power factor, the voltage regulation is negative. Also, we can use primary parameters to calculate the voltage regulation, and also we can use the secondary parameters. But the condition is all parameters must be referred to one side, to the primary or to the secondary. We cannot mix. We use the parameters. All the parameters must be referred to one side, primary or secondary. Excuse me, just 1 minute. Okay. Okay. So here in the exercise, firstly, in the original exercise, they said used the circuit referred to the primary. They didn't add approximate, but I have seen that it will be more simple to use the approximate equivalent circuit. You see here, using the approximate equivalent circuit, you see here that the circuit is the exact equivalent circuit, not the approximate equivalent circuit referred to the primary. In the approximate equivalent circuit, we move this parallel branch, we move it to the input. Why we prefer to use the approximate equivalent circuit? When we use the approximate equivalent circuit, firstly, we neglect the effects of the core. So the excitation current will be not considered. Also, we can add those quantities to each other. So instead of using R1 and R2, or R2 prime, which is referred to the primary, we can use directly R equivalent. R equivalent, if the circuit is referred to the primary, equals to R1 plus A square R2. Also, X equivalent equals to X1 plus A square X2. That's why we prefer to use the approximate equivalent circuit. Approximate equivalent circuit to calculate the voltage regulation in order to do this simplification. So then the approximate equivalent circuit will be like this. We have single resistance, single inductance, like this, and we have primary voltage and secondary voltage referred to the primary. That's why it's multiplied by A and A. We have R equivalent and X equivalent, of course. This one can be R equivalent and this one can be X equivalent. Okay, so to calculate the voltage regulation, okay, here we are using the circuit referred to the primary. So we know that the load is connected to the secondary. So the voltage V2 or AV2 is the voltage across the load, and is equal to what? Equals to 240. It's given in our data. And the voltage, the voltage of the high voltage side equals to what? Equals to 2040. But this voltage is the voltage of the secondary referred to the primary, so it will be multiplied by the turn ratio and it's become to 2400. However, this is the load voltage, the voltage across the load. We know that the no load voltage is different from the voltage across the load. Okay, It's depend on the power factor. Here, the power factor is given at as 0.8. And if when we calculate cosine minus 1 of 0.8, we may have minus 36.8. Also, we may have 36.8. So the angle can be positive or negative. So which one we choose? This is depend to the power factor. So if it's lagging power factor, we take the angle negative because the current is lagging behind the voltage, so the angle is negative. And if it's leading power factor, we take the angle positive because those angles have the same cosine value. But here, since it's lagging power factor, we choose the negative one. Okay. So the current. So what we are looking for here we want to know how it's the no load voltage. We have the voltage across the load, which is 240. And we have referred all the parameters to the primary, so the voltage became 2,400. Mahfoud, you are talking about what?
Sir, when we transfer everything to the primary, so even the load RL, we transfer it also.
Yes, but here we don't need the value of the load. So yes, the load, if it's resistance or inductance, it must be multiplied also by
Okay. Thank you.
Okay, so here we said we have the voltage across the load, which is 240 V2, and when it gets referred to the primary equals to 2,400. The power factor is lagging. That's why we choose a negative angle. We have another problem. The problem number 8. We have different cases. Calculate. We are going to see it, inshallah. Try to find the voltage regulation in different cases, lagging and leading and unity power factor. Okay, so the current is not given, but we can determine the current from the apparent power. Okay. When we talk about this, I was reading a book yesterday, and I found this remark. Generally, in the problems, the apparent power, it's not specified if it's the primary apparent power or the secondary. Always they say it's just apparent power, but always we consider it as the secondary apparent power. Okay, so the current, the secondary current equals to what? Equals to S over V2. S is 150 kVA, V2 is 240, so the current of the secondary is 625 amps. Now, if the current is referred to the primary, it will be divided by the turn ratio, and it's become 62.5, and its phase is minus 36 because it's lagging power factor. Also, of course, the resistance and inductance are given. The secondary resistance is 2 milliohm, and the secondary in the reactance is 4.5 milliohm. When they refer it to the primary, they will be multiplied by a square, which 100. So they become R2 a square R2 is 0.2, and a square x2 is 0.45 ohm. So the current equals to what? Equals to 62.5. Its phase is 36.8, and it can be calculated, can be written in the complex form is 50 minus G 37.5 amps. Okay, so according to the simplified equivalent circuit, we can now calculate the no-load current, the no-load voltage. Okay, so remember this. When we are talking about lagging power factor, which means that always the no-load voltage is greater than the full load voltage. So the voltage regulation is positive. So according to the simplified circuit, we have R equivalent, we have X equivalent. This is the voltage across the load referred to the primary, which is A V2. This is R equivalent. This is X equivalent. And this is V1, which is the no-load voltage. So it's equal to what? Equals to this voltage and plus this voltage drop. So it's equals to AV2, V1 equals to AV2, plus I2 over A, which is the current referred to the primary, multiplied by the impedance, the internal impedance, which is R equivalent plus GX equivalent. Then V1 equals to AV2, which is 2040 plus G0, so its phase it's 0, plus the current I2 multiplied by R equivalent is R1 plus A2, A square R2, and X equivalent equals to X1 plus A2 square, A square X2, and equals to 0.4 and 0.9 respectively. So this is the voltage drop. Now, so V1 it equals to 2045 2453.75 plus G30, and its magnitude is almost 2454. So this is the voltage across the load. And when we calculate the voltage regulation, we use magnitude. So it's the difference between voltage magnitudes. So the no-load voltage is 2454 minus the voltage, the full load voltage, 2040 over 2040. So, and the voltage regulation can be found as 2.25 or 0.225, or as percentage 2.25. So this is the voltage regulation. So I will repeat quickly the steps to calculate the voltage regulation, because this type of question is always repeated in different problems. Okay. So the voltage regulation is the difference, the magnitude difference between the no-load voltage and load voltage. And we said that in order to calculate the voltage regulation, it is preferred to use approximate equivalent circuit referred to the primary or to the secondary. So all parameters must be referred to one side. In this problem, we have choose the circuit referred to the primary, and the approximate equivalent circuit, which is simpler than the exact equivalent circuit. Why? Firstly, the core effect will be neglected, the excitation current will be neglected, and also to have the ability to add those resistance and reactances to each other. Then we must look for the no load voltage according to the simplified equivalent circuit. Of course, according to the equivalent circuit, the no load voltage equals to what? Equals to the voltage across the load, equals to the voltage across the load plus the voltage drop. This is the voltage across the load referred to the primary A V2. This is the voltage drop, which is I2 over A, which is the current referred to the primary, multiplied by Z equivalent, which is R equivalent plus J X equivalent. Then this is the no load voltage. Then the voltage regulation can be calculated as the following. Okay. Now let's see to the second question, which is the efficiency. Calculate the efficiency of the transformer that is operating with 0.8 lagging power factor. We said that the efficiency equals to what? Equals to P out over P in, which is the output power over the input power, and it's equals to what? Equals to the output power over the output power. Okay, hold on one second. My phone is ringing. Okay, let's continue. We said that the efficiency equals to what? Equals to the output power over the output power plus the sum of losses. So the output power can be found from the apparent power, which is the apparent power of the secondary, multiplied by cosine theta, the power factor. So 150 multiplied by 0.8 equals to 130 kilowatt. The sum of losses equals to what? Equals to the core losses plus the copper losses. Okay, since here we don't have the measurement, in some problems they give us the measurement of the no load state and short circuit states. Here we don't have those measurements, but we can calculate it as what? The copper losses equals to what? Equals to R equivalent multiplied by I square, which is the current of the primary square. So it equals to what? The copper losses equals to what? Equals to R equivalent 1 primary multiplied by I2 over A square or I1 square. Okay. The core losses, it can be calculated from the core resistance, since we said that this resistance represents the core losses. So the core losses, since the core resistance is given, so equals to RC multiplied by IC square. So IC is the core loss current that flowing in the parallel branch. So this one. This is IC, the core losses current that flowing in the core resistance. So this is IC. This current IC can be found from what? Since we have the voltage, the input voltage, and we have RC, so this is our RC, of course. This is the input voltage. So this current IC can be determined directly from the input voltage. And RC equals to what? Equals to 10 kilo ohm. So it's 10 multiplied by 10 to the power 3. And IC equals to 0.2453. Always this excitation current is too small. So the sum of losses equals to what? Equals to the copper losses plus to the core losses, and it equals to 2.138 kilowatt. Then the efficiency equals to 120 over 120 plus 2.13 and equals to 0.98 or 98%. So this is concerning the second problem. Okay, if you have any questions before passing to another problem. Is it clear how we calculated the voltage regulation? Okay, great. So, in fact, I didn't prepare all the problems because I consider it as a short meeting. Let's see problem number 8. 80, it's solved in the solution I give you, but I think it's had a good idea about the voltage regulation. Okay. So V load, it's always yes, it is. Yes, it is. Because V load is V2. So when it's referred to the primary, it's AV2. Okay. Yes. You are talking about AV2. Hold on a second. Okay. Please repeat your question because I left the meeting and I get back. So the chat box has been cleaned. You have to, yeah.
So I said that VLOAD, it is always AV2.
Yes.
You answered yes. Does it mean that it is always equal to the rated value of V1 because AV2 is equal to V1? And we have the
yes,
value.
Because the rated value it's at full load. For example, it's given at full load.
Okay, so if it is not at full load, it will be another thing.
You know, normally the values that given in the nameplate of the transformer generally are the values at full load, the rated values generally.
Okay, thank you.
Okay, let's see problem number 8. It's similar to the previous problem, but we have different cases of the power factor. Okay, so 75 kVA, 2400 volt and 240 volt, 60 hertz distribution transformer has equivalent resistance and reluctance. So they are talking about what? About R equivalent and X equivalent directly, so respectively, which are both referred to the secondary side. So in this case, it's the secondary side. So the condition, we said that it must be referred to a single side, primary or the secondary. Determine the full load voltage regulation at 0.55 lagging power factor, at unity power factor, and at leading power factor. Okay, so let's see the equivalent circuits referred to the secondary. So here it's simple because they give us directly R equivalent and X equivalent. So this circuit referred to the secondary, this is R equivalent. This one is X equivalent. So you know that the value of R equivalent and X equivalent is different in the secondary. R equivalent equals to R1 over A plus R2 over A square, sorry, plus R2. But here they give us directly, the values of R equivalent and X equivalent. So the voltage across the load is V2. This is the voltage across the load is V2, and this is the voltage V1, which is the no load voltage V1 over A, because it's referred to the secondary. According to this circuit, V1 equals to what? Oh, V1 over A, which is the no load. We said that to find the voltage regulation. I repeat the same things in order to save it in your mind. It's full load or full load voltage minus no load voltage over full load. Okay. So we are looking for this one, the V full load, and in this case it's equal to what? Equals to the voltage V1 over A, because the circuit is referred to the secondary, minus V2 over V1 over A. Okay. So okay, no over full load. Sorry. So it's V2. The voltage across the load is V2. So this voltage equals to what? Equals to V2 plus the voltage drop. The voltage drop is I2, the current multiplied by the impedance. I2 equals to what? I2, it can be determined from the apparent power, which is S. So we take it as a rule. The apparent power is the secondary apparent power over V2. So I2 equals to 312.5 amps. Since the power factor is given as 0.8, the angle, so the cosine minus 1 is 31.79 degrees. And because it's lagging power factor, we take it as negative. So the voltage is the voltage across the load is 240. 40. Its phase is 0, and the voltage drop equals to what? Equals to the current. This is the current I2 multiplied by the impedance. So the values of this is I2 multiplied by R equivalent, and here it's I2 multiplied by X equivalent. Then the voltage V1 over 2, which is the no load voltage, equals to its magnitude is 252.48 or 49 volt. So we see that the no load voltage logically is greater than the load voltage. So because it's a lagging power factor, when we connect the load, the voltage gets dropped. Then the voltage regulation equals to what? Equals to 252.48 minus 240 over 240, and it's equal to 5.2%. This is the first case. The second case, at unity power factor, the cosine phi is 1, so the angle is 0. Then the angle is 0. So see here, it's a unity power factor, but it looks like the lagging power factor because we have the internal also inductance of the transformer. So I2 is not shifted, so the angle is 0, but V1 equals to what? Equals to V2, which is the voltage across the load, plus the current I2 multiplied by the internal impedance. This is R equivalent, and this is X equivalent, the internal impedance of the transformer. So here, the difference between the no load voltage and the load voltage is not huge. Then the voltage regulation is equal to what? To 2, in similar way, of course, equals to 243.59 minus 240 over 240. So it's 1.5%. The third case at leading power factor, so it's the same power factor. Here the angle has been taken positive. The angle has been taken positive. Of course, here to multiply the current by the equivalent impedance, this must be written in complex form. You know how to transform it to the complex form. Then the voltage, the no load voltage equals to what? Equals to 240 plus the voltage drop. Here, in this case, the voltage drop delta V is negative. Okay. So that's why the no load voltage is In fact, the voltage drop is positive. When we move it to the other side, it's become. In fact, it's positive. When we move it to the other side, it's become negative. Okay. So here, the no load voltage is less than the load voltage. And this case, when we have a leading power factor, for example, when we have leading power factor, for example, when we connect a capacitors to the output of the transformer, and here the voltage regulation is negative. It's 233.47 minus 240 over 240, and it's equals to minus 2.72%. So this is the problem number 8. I just solve it because it's solved in the recitation, but I just solved it to see the different cases of the power factor and the difference between this problem and problem number 4. Here, the circuit is referred to the secondary. Okay, so I hope those problems was clear. I will stop here by this problem. I will try, inshallah, to organize another session. I don't know when. Maybe this week, inshallah. If I couldn't, inshallah, next week we are gonna back regularly, inshallah, to our sessions. Okay. If we say half load, just the load will be divided and the voltage and the power. If we have half load, we have different calculations. Some, for example, the power and the core losses, the copper losses. There are some things will be changed. We have a problem in like this, in case of half load. We're gonna see it, inshallah. If we don't have a load, it's open circuit. You know, when we have open circuit, we have voltage, but we don't have a current. Okay, but if we don't have a load, there is no voltage drop because the current, if we don't have a load, the current in the secondary, we don't have a current. And in the primary, the current is too small. I mean, if we don't have a load, okay, yes. If we don't have a load, the secondary is open. There is no current in the secondary. And in the primary, we have only the excitation current. Okay. When we if it's open circuit, we don't talk we don't talk about Z equivalent, because the current, well, if it's no load, the current, all the current will go to the parallel branch. So it will be all the current is the excitation current, I0 or IA. So we don't have. Go back to the transformer test. See that in the open load, open circuit test, we didn't talk about R equivalent or X equivalent. Okay, how we know it's lagging or leading? Okay, this they must tell you. Okay, they must inform you if it's lagging or leading, of course. Or maybe they give you a hint. Maybe they give you. Maybe they give you a phasor diagram, for example. So if they give you a phasor diagram, you can know that it's lagging or leading power factor according to the angle. So Asil, when we have open circuits, we don't have a current. We don't talk about Z equivalent at all. Okay. Yes. We did use it to calculate V2. I didn't get your question.
Sir, excuse me. I'm sorry because I'm a little bit confused between V2 full load and V2 no load. Can you show us, please, one more time how we calculated the V2 no load?
Okay. In our in those problems. Okay.
Yes, in the problem, exactly. In problem, the first one, I think, number 4.
Okay. Number 4. Okay. The no load. You are talking about the no load. Okay.
Yes, please.
The no load, we have used the approximate equivalent circuit. Here, the no load. So when we use, so V2 is the voltage across the load. If we don't have a load, for example, if we don't have a load at all, if we don't have a load, this is the circuit, for example, this is Rx. Okay. If we don't have a load, this is the voltage, no load voltage, which is V1. For example, it's referred to the primary. This is the voltage across the load, V2 or V2 times A. If we don't have a load, they will be equals. Okay. If you don't have a load at all, they will be equals because there is no current, or the current is neglected, so there is no voltage drop. So there is no voltage drop, so it's because they are parallel. So if there is no voltage drop here, they will be equal.
Yeah, so they will be equal here.
Yeah, yes, they will be equals.
Can you continue just the presentation to see?
Okay.
Because then, I think I got it wrong.
Okay. Then, so we have used the approximate equivalent circuit to found according to this circuit. So if we have a load, so okay, I will draw the load to don't confuse, so don't get confused. So we have a current. So the current circulate here. It's I1 or I2 over A. So it's I1 or I2 over A, which is equals to 62.5. So it has been found from the apparent problem. So the no load voltage equals to what? Equals to the voltage across the load plus the voltage drop, which is Z equivalent. So in this case, we are, okay, look.
But it is no load, no, sir.
Look, so do not get confused.
Yeah.
So it's no load voltage, but it's no load. It's no load voltage, of course. But how I can give it to you? So, here we have a load. It's not. We are not in the open load state, but we have a load. But we need to find the voltage to what if we remove this load? Okay, how the voltage will change? How the voltage become? Okay. So it's the, let's see, say it as the input voltage. Here in this case, it's the input voltage.
So it's not V1, like it's different. I'm just I didn't get it because in my head I see it like they are parallel and AV2 equal V1. But here we have the current, yeah.
But okay, so here when I said it's no load voltage, we are not talking about the no load state. If we don't have a load, if you don't have a load, they are equals. But in this case, since we have a load, okay, so imagine that we don't have a load. When we connect the load, the voltage get changed, okay, because of the voltage drop. But here, the no load voltage is the voltage before connecting the load. That's it. V1 is the voltage before connecting the load. So imagine that you don't have a load. The voltage there equals because we don't have a current. When you connect this load, the voltage gets drops. But V1 is the voltage before connecting this load. Why? Because we have such current, then we have a removed. Okay, we have such current. Okay, so we normally before connecting the load, it was like this. Before connecting the load, it was V1 equals to IV2 before connecting the load. When we connecting the load, we take that voltage drop from V1. Okay. If when we connected the load, the voltage drop happened. So we have taken a small voltage amount from this original voltage. So this voltage equals to what? Equals to AV2 plus that voltage drop. Okay, so it's the voltage before connecting that load.